visualizations, so hopefully the modeling community will appreciate them. Basically, we have a pilot array of deep Argo floats in the Australian Antarctic Basin. So I'm going to show you what they've observed over the past 2 years. Oh. Okay, so real quickly, I'll just go through some motivation, but I think everyone in this talk should have a sense of why we care about Antarctic bottom water. But anyway, in the Australian Antarctic Basin, which I have kind of outlined here in red, the bottom water is actively ventilated from 2 source regions. So you see this blue tongue coming out of the Ross Sea and another blue tongue of high CFC values coming out of the Adelie Land. But it's also been changing over the past several decades. And this is based on repeat hydrography sections. So maybe once every couple years or even once every 10 years, these measurements are made. And you see that the figure on the left, that the Australian Antarctic Basin outlined in blue there is one of the reddest spots in the world. So it's warming the fastest for waters deeper than 4,000 meters. And then on the right, you see these little red bars that get kind of progressively larger, meaning more warming seen in the bottom 300 meters as you go around the pathway of bottom water. And it's also been freshening. So that same figure with the bars, those blue bars are the salinity trends. And you see that it's really strong changes in salinity near the source water regions, so near the Antarctic coast, and then it gets progressively less change as you go along the pathway. And you also see in the figure on the left, another paper by Sarah Perkey and Greg Johnson, where you see a lot of freshening in the Australian Antarctic Basin. So it's a region of a lot of change, and it's globally important in terms of the meridional overturning circulation and sequestration of carbon and heat into the deep ocean. You can also look at the changes in a different way on a TS plot. So this is just from that region along SR3 at 140 east, south of 60 south. And you see from the 60s, late 60s, early 70s through 2011 that it's been steadily freshening in particular. So those lines are to the left as you go through the years. Yeah. So I'm going to look at the pilot array of deep Argo floats and sort of try to answer these questions of how does the observed variability along these repeat hydrography sections compare to that in the basin as a whole? And then are the long-term trends that we see based on very limited observations within or outside the range of even just the seasonal variability within the basin, which we've now observed for the first time. And so the array is made of 12 floats right now, with the idea to deploy more and more once we can get back down there on the ship. Most profile on 10-day cycles after initial testing near the surface. They park pretty deep, so generally deeper than 3,000 meters, but it's slight differences depending on how the people that are piloting want to do it. And so what that allows is for most of the floats to have remained in the basin, aside from that one orange triangle Arbor float that sort of went on its own adventure off to the east. The floats are also equipped with an ice detection algorithm so that they can profile under the sea ice throughout the winter. So we have profiles from under the ice over winter for the past two winters. And we can refine the standard linear interpolation under the ice with information about how deep it profiled, and then using the bathymetry, we can sort of shift them latitudinally along the slope, especially where there's big changes in depth. And then finally, they have a shipboard CTD is taken with each one on deployment. Then that's used for calibrating the salinity. So I won't get into the details of the calibration. If someone wants to talk about it after, they're more than welcome, but I figured for this audience, you probably don't really care about the nitty-gritty. And then just as a note, the solo floats, so the circles and diamonds in this figure, profile as deep as 6,000 meters, and the others, the arbors and the ninja float, which are triangles and the square along the slope there, can only profile to 4,000 meters. But that often gets to the top of the Antarctic bottom water layer anyway, so we can still measure the thickness. So if you just simply define Antarctic bottom water as any waters denser than 28.3 kilograms per meters cubed of neutral density, and you look at all the floats for the top panels and the bottom left, it's all the floats that sampled Antarctic bottom water and reached the bottom. So it's the average of those properties, salinity, temperature, and density over the entire bottom water layer. Whereas the one on the right, the float only had to reach the very top of the layer for it to be included in this analysis. So you see a bit of a suggestion of this bimodal distribution in salinity, where you have sort of saltier, more saline waters coming from the Ross Sea. And you also see a bimodal sort of distribution in the density of the layer. And on average, so you have this denser version and a slightly lighter version of Antarctic bottom water in the region. And on average, about 500 meters, but that varies a lot in space, which I'll show you now. So this is just the number of profiles that reach the bottom, which is not very exciting. And then you can map out in each of those little boxes, you can average here's the salinity of the bottom water, and you do see this sort of saltier version of Ross Sea bottom water coming out in between 150 and 160 east, and then a slightly fresher version of Adelie land source bottom water coming out near 140. And then the picture is very similar to look at where you see sort of warmer version near the Ross, coming from the Ross Sea, colder coming from the Adelie land, and then much warmer temperatures north of about 62 south. But what you see along those southern boxes is that those two source waters are actually compensated in density. So they have pretty similar densities there, and you just see that you get progressively less dense waters as you go around this path, with the really light waters, again, kind of north of about 62 south. And then in terms of thickness, you have just about 150 more profiles that reach the top of the bottom water layer rather than the sea floor. So there's slightly more data. So there's a bit more data that goes into this map. But what you see is a sort of thickening of the bottom water layer as you move west along the slope, with the thickest values near 120 east. And that's getting up higher than 1,000 meters of bottom water in that region as it sort of pools up on the end of the slip there. And then you see thinning as it spreads and mixes to the north. And then just as a final bit, getting back to this kind of comparison with properties along SR3 at 140 East. You see, so these scales are the same, and it's a bit hard to compare, but what you see is that the spread of the values observed just between 2018 and 2020 is similar to the spread of values that you've seen since 1995. So you don't see those values from the late 60s, early 70s, but you do see quite a spread along 140, and this is just, again, south of 60 south and near 140. And then I've highlighted the summer profiles in red here to show that there is a bit of seasonality in that the summer profiles are very clearly more fresh than the winter profiles, which are what you see here now in blue. So there is some seasonality in the properties of the bottom water in this region. And so one of the main points that I want to make here is that we have very limited shipboard observations in this region of the world, and that this pilot array was really going to elucidate a lot of and illuminate a lot of information about the deep ocean and the entire water column in general, because of course it profiles the entire water column. That will allow us to put these long-term trends into a broader context. And so in conclusion, there's this really exciting array of deep profiling, full depth or nearly full depth, year-round under ice data set of CTD profiles. And that even at sort of a first pass, you can see two distinct sources of Antarctic bottom water that are compensated in density. So you have the colder and fresher Adelie land sourced versus the warmer and saltier Ross Sea sourced bottom waters. And then the historical changes that you see along 140 since the 90s are similar in range to that you see in the local variability in the same region just over 2 years, with the freshest bottom waters in summer and the more saline in winter. And so I will maybe question or challenge the COSMO community to ask, how well do the models capture the variability of bottom water in this region? And that's probably more of a naive question because I have not looked at all in the model, so someone might know that off the top of their head. And then what sort of temporal variability do you see? Do you see a strong seasonal cycle? And how can we use the model to really fill in some of the gaps in this pilot array? Because there are many. Because for one, we can't tell the floats where to go. They drift where they want. And there's still only 12 of them, and it's a big region. So that's that. Thank you. And I can take any questions.